Okay, so in this lecture we'll do a little example to demonstrate the power of the primary decomposition theorem. In the last lecture video, I stated the primary decomposition theorem without giving a proof. But what does it say? So it tells you a general statement about any arbitrary square matrix. So we know that not all square matrices are diagonalizable. So not every square matrix is similar to a diagonal matrix. But it turns out that every square matrix is always similar to a block diagonal matrix, and this is very closely related to the Eigen Spaces. So it says that given any n by n matrix T, or given any linear transformation T, we can decompose Rn as a direct sum of k T invariant subspaces, and each T invariant subspace corresponds to one block in the block diagonal matrix. And how do we obtain these T invariant subspaces? We obtain it using the minimal polynomial. So the minimal polynomial can be decomposed as a product of powers of irreducible polynomials. So if we can write P of x equal to P1 of x to the R1, P2 of x to the R2, and so on, PL of x to the RL, then Vi is equal to then the ith T invariant subspace is the null space of Pi of A whole to the Ri. Okay, and let's see an example to understand this better. All right, so on the left I have a little example. So this is the matrix that we'll be working with. Okay, it's a 4 by 4 matrix, and the entries are given as follows. Okay, I've also written up a little function which helps me compute the powers of matrices easily. So mat pow of a comma n gives me a raised to the n. Right, so it just prevents me from writing matmul multiple times. Okay, so now let's first check what the eigenvalues of A are. Right, after all, we want to compute the minimal polynomial, right? And so let's find the eigenvalues, right? And what is that equal to? So np dot eig of A 0. So this gives me the eigenvalues. Oops. So this should be ln eig. Right. So well, it's roughly, let me call this equal to this, and so let me make this look a little better. Okay, maybe it's better to just write. Okay, so the eigenvalues are just 2, 2, 1, and 1. Right? So it has two eigenvalues equal to 2, 1. So the distinct eigenvalues are 2 and 1. Right? And okay, so we have this, and so the algebraic multiplicity of the eigenvalue 2 and the eigenvalue 1 are equal to 2. Now if this matrix were to be diagonalizable, then one way to check would be to find the arithmetic multiplicity and the geometric multiplicity, and verify that the two are the same, right? So maybe let's just look at the geometric multiplicity of the eigenvalue 2. So how do we find the geometric multiplicity? You compute A minus lambda I right? The geometric multiplicity is the dimension of a minus lambda I. So in this case, it is a minus 2i, right? So let's find the rank of a minus 2k, right? It has rank 3. So this has rank 3. Therefore, the nullity of this particular matrix is 1, right? And therefore, the geometric multiplicity of 2 is equal to 1, and this is not equal to the algebraic multiplicity, right? And therefore this matrix is obviously not diagonalizable. So it's not diagonalizable. So let's see, so can we block diagonalizers, right? The hope is to somehow show that this is similar to a block diagonal matrix with at least 2 by 2 blocks. Okay, so let's first compute, let's see what the minimal polynomial is, right? So one way to do this is to have np dot. So I want to find, okay, so clearly if a minus I, right, so I want to find the minimal polynomial p of x, right? And this is x minus 1 raised to alpha times x minus 2 raised to beta, because 1 and 2 are the eigenvalues, and alpha can be either 1 or 2. Both alpha and beta could be. So the question is this 1 or 2? Right? Because clearly x minus 1 the whole square times x minus 2 the whole square is equal to the characteristic polynomial. So the characteristic polynomial f of x is x minus 1 the whole square times x minus 2 the whole square, and we know that f of a equal to 0 from the Cayley-Hamilton theorem. Now if the matrix were diagonalizable, then we know that the minimal polynomial would have been x minus 1 times x minus 2, but clearly it is not equal to the minimal polynomial. Sorry, so this is clearly not the minimal polynomial, because if it had been the minimal polynomial, then the matrix would be diagonalizable, right? So obviously maybe this is 1 and 2, or maybe this is 2 and 1, or it's 2 and 2, right? Let's check that out. So I'm going to find power. So this is a minus I raised to 1 comma a minus k1, right? So clearly this is not 0. So this is a minus, this should have been 2i, right? So a minus I times a minus 2i is not equal to 0. So let's look at, so a minus, this is a minus I. What I computed here is a minus I times a minus 2i, which is non-zero. Let's next compute a minus I the whole square times a minus 2i, right? This is also not equal to 0. Let's look at a minus I times a minus 2i the whole squared this is also not equal to 0. So a minus I times a minus 2i the a minus I the whole square. This is obviously equal to 0 because it is equal to the characteristic polynomial. Right? So therefore this is indeed the minimal polynomial. So the minimal polynomial of a is equal to x minus 1 the whole square times x minus 2 the whole square. Right? And from the primary decomposition theorem, we know that V1 is the null space of a minus I the whole square, and V2 is the null space of a minus 2i the whole square. Right? So let's try to compute the null spaces of these two. Right? So let's first look at a minus I the whole square. Let's call this a1. Right? And what we want to find is the null space. So one way to do this is to do row reduction on this particular matrix. I'll make my life easier by doing LU decomposition. LU of 1. Right. So this is my LU decomposition. Let's to 0. All right. So so this is our LU decomposition. Now clearly this and this are the pivots, and these are the non-pivot variables, right? So x2 and x4 can be chosen as non-pivot variables. So these can be taken as my free variables, right? And this has dimension 2, so the nullity of a1 is 2. So nullity of a minus I the whole square, this is equal to 2. Okay. So let's see. Can we guess one particular vector in the null space? So let's take V1 to be so clearly so from this equation x3 minus x4 should be equal to 0. So 0.166 x3 minus 0.166 x4 should be equal to 0. So x3 should be equal to x4, and if I take this to be 1 1 1 1, then is this satisfied? So x3 plus x4, so this is equal to 0, this is 0, so yes. So u times the all ones vector is equal to 0, right? So of u comma array of Oops. Right, so I get the all zeros vector. So that is fine. Can I guess another vector which satisfies this? I can choose 1 1 0 0. That's one option. Can I choose something else? 1 1 minus 1 minus 1. How about this? Yep, this is also equal to 0. So I'll choose my v2 to be equal to 1 1 minus 1 minus 1. Okay, so fine. So this is easy. Now let me do the same for a minus 2i the whole square. Print it. Right, okay, so I get something like this. So I want to guess a particular vector over here. So I want to guess a vector in the null space. How about 1 minus 1 1 minus 1? Yes, so this vector indeed satisfies u times v3 equal to 0, and therefore a1 sorry, let's call this a2. Okay, this is a2, 1 minus 1 1 minus 1, and so that is fine. 0 0 0 0, and here's another v4 equal to 1 minus 1 minus 1 1. So this is also equal to right, so this is also equal to 0. If I take something else like this is not 0, right? Okay, so I have four vectors. v1 and v2 form a basis for v1, and v3 and v4 form a basis for v2, and therefore so if I write all of this in the form of a matrix, so my P matrix is going to be one 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 one. So this is my first column. I'm going to take a transpose later, and 1 1 minus 1 minus 1, and 1 minus 1 1 minus 1, and 1 minus 1 minus 1 1. Okay, now it's 1 1 1 1, which is v1, 1 1 minus 1 minus 1, which is v2, 1 minus 1 1 minus 1, which is v3, and 1 minus 1 minus 1 1, which is v4. So let's just check that this is indeed a basis. P matrix rank of P, so it's 4. It's a full rank matrix, and for this to be diagonalizable, we need to verify that P in P D P P A P inverse. So So A should be equal to P D P inverse, or our block diagonal matrix D should be equal to P inverse AP. Let's verify that. NP dot null of NP dot in of P. So P inverse times A times P. This is P inverse AP, and this is indeed a block diagonal matrix, right? It has two blocks, 1 1 0 1 and 0 0 2 2 0 2. Okay, so this is a way to find the block diagonal matrix which is similar to our given matrix. Okay, so essentially what did we do? We first found the eigenvalues of A, and we found the minimal polynomial. So the goal was to find the minimal polynomial as a product of irreducible polynomials, P1 of x to the R1, P2 of x to the R2, and so on. And then we find the null space of P1 of x, sorry, P1 of A to the R1 to the R1, the null space of P2 of A to the R2, and so on. Right, so basically we want to find basis vectors. So this will give us v1, v2 something, and then say v3, v4, and so on. So once we find a basis, so we stack all of these vectors v1, v2, v3 up to vn. This gives us our matrix P, and the block diagonal matrix would be equal to P inverse AP.